So there was a connection loss. All are connected, right? Can you hear me? So as I mentioned, so in combinational circuits, we are creating the ALU. In sequential circuit, we are creating the memory. So for combinational circuit, the output is only depend on the present input, and here the output will depend on the previous output and the present input. So by doing this feedback, uh, we can save a particular bit in this state, right? So we need to set that particular state. We can use this reset and set, right? If we need to access that particular state, but we can use this 0, 0. When this 0, 0 given as a input, the output will be the saved particular state, right? The saved state, right? So from reset, we are saving 0. From set, we are saving 1, right? So for using this circuit, we can save 1 bit, right? In this circuit, SR. Right. So I will again. So what will happen in combination circuit? We are creating the ALU. ALU is arithmetic and logical unit, and in sequential circuits, we are creating the memory. So by using this present input and the previous output, here combination circuits, it will only depend on the present inputs. So this is the SR latch. So that means there are set and reset inputs, and outputs are Q and Q bar, right? So we can draw the SR latch by using two NOR gates or two NAND gates, and the truth table is this S and R. So there are 4 states: 0, 0, 0, 1, 1, 0, and 1, 1. So 0, 0, there will be no any change to our previous input. That means if this is 0, then the Qn plus 1 also 0. If Qn is 1, Qn plus 1 also 1. So that's why we are saying for 0, 0, there will be no change to our previous inputs, right? For reset, the Qn plus 1 will be 0. That means if this is 1, it will set to 0, and our Qn plus 1 will be set to reset. So Qn plus 1 will be set to 0 in reset. Then Qn plus 1 bar is set to 1 in set state where S is 1. Then our Qn plus 1 will set to 1, and Qn plus 1 bar will be set to 0, right? So this is our SR latch. So next we need to identify why we need the clock. So So clock is something right. So there are another terms that is clock ticking, right? So this particular cycle, there is a rising edge and there is high state, falling edge, and low state. So this particular uh, thing will name as the clock tick. So clock tick will only occur where there is a rising edge, right? So as I mentioned, the clock tick will only occur where there is a rising edge, right? So what that means is when there is a clock tick, then only this output is going to change, right? So now we have actually three inputs that are our set and reset and the clock tick. So if you have the lecture slides with you, you can see the gate as well. So I will draw it. Right. So we need to integrate the clock as well. So since, as I mentioned, uh, actually in this rising edge, that pair the clock tick. So that means the value is high. So that means this should be need to be true. That means it should be need to 1. So that's why we are integrating 2 AND gates. So this is actually our clock. Normally we know it as C. Oh, this is S and this is R. So this is the sub flip flop, right? So as I mentioned, now we need to consider this is the truth table for SAR latch. So S and R, where S is 0, 0, output is no change. S is 0, the R is 1. That is reset state. Then the if it is reset, this then the Qn plus 1 is 0. And in set state, that means S is 1, R is 0. So in set, our memory Qn will true, right? So the last occasion, the both will be uh, either 0, 0 or 1, 1. So we are saying it is undefined, right? So how to integrate the clock? By using 2 AND gates. So here we are getting our clock sync. So this state will going to only change where the clock ticking is happening. So what that means is this. So high states showing the where it is 1 and low states showing where it is 0. our clock. Actually our clock comes. So what you need to decide is the Q. So you need to consider this one. The thing is, if this clock is 0, in this state the clock is 0. In lower state the clock is 0. So in that case the output of this one will always 0, right? So that means if the clock is 0, according to our truth table, it is in the no change state, right? So that means it will keep sending the previous output as the present output, right? And the only the set, reset, and again the memory also going to check the where this clock tick is happening. So that's why I do it like this. It actually this SNR need to be a little bit uh, a particular time before. Otherwise, it cannot recognize this rising, right? That means let's consider clock is also this, and our SNR also something like this. So this clock ticking and this rising happen in the same time. If this is happening the same time, actually the clock can't figure out actually the value. So there should be a little bit time ahead to actually identify this is 1 or 0, right? So in this particular case, the both are 0, right? So, so since this is also starting from 0, in this case also it will continue, right? Because it is get the previous state, right? In this particular scenario where this tick is happened, our previously our Q is 0, right? This is the previous Q. So since it is 0, the next Q also will 0 up to this tick. Then what will happen? Then there is a set, right? So set means this is going to be 1 up to this clock tick. Again set, right? And now reset. Right? So here also reset. Then what will happen? Then actually it is undefined state. So we are marking this fourth one. And we are saying this is undefined. Let's consider this particular part is 1. Then what will happen? If this is 1, where happen the clock tick happen, SNR is 0, 0. Then it is in no change state. So then since this is 1, up to this clock ticking also this the Q will be 1, right? So you need to do this also. That means you need to continue this Q. What will be the output by giving this kind of a timing drop? This is where the clock tick is happened, and the outputs, our input S and R. Then the previous output is the sometime before, right? So based on that, you need to fulfill the whole graph. So you can draw the truth table for this ones where S, R, and our clock. So that means 3 variables, that means 8 occurrences, right? Right. And the power of Q and plus 1. So try to draw this one. Draw this to truth table based on this one. So there should be 8 occurrences. And it's enough for you to mention only the Q and plus 1. You don't need to mention Q and plus 1. So what I ask you to do is, so as I mentioned, this clock ticking. So clock ticking means this cycle where when the falling is happening, when a clock tick will only occur where there is a rising edge. So this is rising and this is falling, and this particular circle will known as a particular clock tick, and only the clock tick can change the output. So this is the SR flip-flop. This is the SR flip-flop by integrating the clock cascade. So since we are integrating the clock, that means the output can only occur where there are clock ticks. So that means the clock should be true. So that's why we are integrating the clock by using 2 AND gates. And then you need to able to draw this timing graph where you give in the S and R in as a digital wave, and this is the clock stream, and you need to able you need to draw this Q or the output code where the clock is happening, and based on the previous output. So previous output will be this one, right? So if this one, if the previous output is 0 for this particular portion, and here you can see the SN, both S and R is 0. So that means this is not going to be changed. So if this is 1, if this is 0, then it's not going to change for next clock ticking is happening, right? So now you need to draw the this truth table using the clock as well. So we have 3 inputs, SR and the clock, and you need to draw the QN plus 1. Right, I think you can draw this one. And again, you can draw the circuit based on the previous output, that is QN as well. So it is in your tube test like this. So there is another circuit. So that is the JK flip flop. Yeah. So due to the time being, so I will stop it here. Yeah. Yeah, we need to cover JK flip flop and the binary counter and D flip flop. So actually, D flip flop is used to create the memory. So it has only the one particular input called data line. So yeah, I will do it in next week. So I think you have clearly I need to cover. So please in home, please draw this table as S R and QN, and the output is QN plus 1. So there are 3 inputs, SR and QN, and try to derive this QN plus logical. So I have teach you how you can decide, and in this truth table you can decide how the clock is working. Uh, right. So do you have any questions? ප්‍රශ්න තියෙනවා? So here I only teach you about this SR flip-flop and SR latch using only NOR gate. So you can learn about how to do this using NAND gates. Please do that, right? So they are going to be only these truth tables will be same, and only some small differences in this S and R and Q. Right, we can stop here. If you have any questions, please ask. Yeah, you can use the Q bar as well, but normally we use the Q. Like as I mentioned, to create the memory, we use D flip-flops. And where the D flip-flop, we are only using the Q. So thank you, students. I will wind up the session here.